Welcome to our unit on chemical quantities and the mole concept. In this unit, we are going to be doing chemical calculations. If you think about it, many of the materials that are around you right now were made by people. To make those things, the chair you're sitting on, the table that maybe you have a computer sitting on, the carpeting in the room or the tile on the floor, the dye that makes up your shirt, those things are made of chemicals. And so the people that made them use chemical reactions and chemical processes. If you want to make something economically and efficiently with as little cost and as little waste as possible, then you need a method of calculating how much chemical you need to start the reaction and how much chemicals you expect to be produced. So that's what this unit is about. It's about how to calculate using chemical quantities, and we are going to introduce you to a special quantity in chemistry called the mole. If you watched the previous set of videos that I made about chemical equations and chemical reactions, you'll recall that the relationship is the way that you look at them. Atoms react in real life. And when they do, this is important. They do so individually or in small groups. We represent those small groups or individual atoms on paper with chemical equations. And those equations should be balanced. They should not only tell us the chemical formulas of the substances involved, but also their relative amounts or proportions or ratios. How much of one substance do you need? How much of another substance can you expect to produce? For example, here's an equation that is already balanced. It shows hydrogen and oxygen reacting to form water. And if you read this on a molecular level, what this equation tells you is that 2 molecules of hydrogen gas, H2, and 1 molecule of O2, there's no 1 coefficient, but it's implied, react together to make 2 molecules of H2O. Now the problem is, if I wanted to make water, I cannot actually count out individual hydrogen or oxygen molecules. Molecules are just way too small and way too numerous for me to see or count. For example, I spilled 1 milliliter of water, that's 1/5 of a teaspoon, on a student desk. And I calculated that if I counted to 1 trillion, and then I did that 30 billion more times, that's about how many water molecules are on that desk right now. Water molecules, all molecules, are incredibly small and incredibly numerous. So we need some way to cope with that. And that's where we're going to be bringing in the concept of the mole. So before we get to that, let's take a look at this again. If I wanted to make a certain amount of water, but I can't actually count the molecules, what could I do to get a certain amount of water? I'm going to need a substitute for counting. I'm going to need some way to count without actually counting. There's got to be a way to determine how many molecules we either need or are going to expect to produce without actually having to enumerate or count them. Here's an analogy. Here's a stack of paper on a tabletop. How many sheets of paper are in this stack? Can you think of a way to count this paper without actually having to count 1, 2, 3, 4, 5, etc.? Well, how about this? What if I knew how much one sheet of paper weighs? Then I could weigh the entire stack. I could do a short calculation and I could count without actually having to count. I would count by weighing or by taking the mass of this stack of paper. So maybe we can use mass somehow. If we look at the balanced chemical equation again, maybe instead of saying 2 molecules of hydrogen, I can say 2 grams of hydrogen. Let's say I wanted to make 2 grams of water. Well, if I insert the word gram there, 2 grams of H2 and 1 gram of O2, that doesn't give me 2 grams of water, it would give me 3. So there's something not quite right about that process. And what's going on here? What's going on is that oxygen atoms and hydrogen atoms don't have the same mass. 2 grams of hydrogen gas actually has 32 times more atoms. I need a 2-to-1 molecule ratio, but instead I'm getting a much larger ratio of hydrogen than oxygen. It's kind of like comparing grapes and apples. If I had 1 pound of grapes, I would have a lot of grapes. But if I have 1 pound of apples, I might only have 2 or 3 apples. So I can't just use weight or mass directly. I can't just insert the unit grams into an equation and make it work. But I know with the paper example that I can use weight or mass as a substitute for counting. So there's got to be a way to do that. How about this? What if I knew that 3 apples weighs 1 pound? What if I had a small basket of apples and I found out that it weighs 4 pounds? How many apples are in the basket? Well, if I know that 3 apples equals 1 pound, then if I had 6 apples, that would be 2 pounds. If I had 9 apples, that would be 3 pounds. And if I had 12 apples, that would be 4 pounds. So there are 12 apples in the small basket. Mathematically, we could have determined the number of apples using an equation. What we would do is take the equivalence, 3 apples equals 1 pound of apples, and make that into something called a conversion factor. A conversion factor is a fraction, and you use it in a multiplication problem like this. Let's write down what we're given on the left side of our paper, 4 pounds of apples. On the right, let's write down what it is we're trying to find. We want a count or number of apples. There's got to be a way to convert pounds of apples into numbers of apples, and we do that by using a conversion factor, a fraction that equals 1. 3 apples equals 1 pound of apples. So even though this fraction doesn't look like a 1, it actually is. 3 apples on top and 1 pound of apples on bottom are actually the same thing. If you have the same thing on the numerator and the same thing in the denominator, then that fraction is equivalent to 1. And I can multiply anything I like by 1. So I can multiply 4 pounds of apples by 1, and what it's going to do is convert it from pounds of apples into a count. In order to multiply this fraction, it may be easier for you to think about the 4 pounds of apples as a numerator over 1. And now you multiply the numerators, multiply the denominators, and gather them together. And you can cancel out anything that appears in both the top and the bottom of this fraction. Since everything is multiplied in the top and everything's multiplied in the bottom, we can simply divide out anything that's in common. So pound of apples, I'm going to mark that out. And what I'm left with is 4 times 3 apples over 1 times 1. In other words, I have 12 apples in my numerator. I have the number 1 in the denominator. That's equivalent to 12 apples. So by doing a short little equation, I can convert number of pounds of apples into a count of apples. Let's see if you understood that process. What if I had a bigger apple basket, a bushel basket, and it weighs 35 pounds? How many apples are in the basket? Why don't you pause the video and see if you can figure this out using a conversion factor of 3 apples equals 1 pound of apples. Here's the solution. I write what I'm given on the left side of my paper, 35 pounds of apples, and I'm going to go ahead and put that over 1, make it look like a fraction. I want to find a count of apples, and so I write that on the right. I got to keep my target in mind, and so I always write down everything. I write down apples, and now I look for a conversion factor, an equivalence. Turns out 3 apples equals 1 pound, so I make that into a fraction like this. The pound of apples on top and bottom are going to cancel. I have 35 times 3 over 1, and that equals 105 apples. So by weighing my apple basket and doing a short calculation, I actually got a count of apples. I apologize for those times that you can hear the dog barking in the background. I don't have time to go back and fix that, so we're just going to have to press on here. If we want to use this conversion method with atoms, then we need to know how much they weigh. That's going to be really important. More specifically, we need to know how many atoms are in a given amount of weight. Fortunately, we have a fairly simple way of determining this equivalence. I say simple, it's going to turn out to be simple in the end, but let me explain it. It is rather complicated in the middle. Here's what you have to understand. Even though atoms are different from one another, they're made of the same basic parts: protons, electrons, and neutrons. Now, even more interesting than that is the fact that protons and neutrons have almost equivalent masses. So that's going to simplify our calculations. If an atom weighs something different from another atom, it is because they have a different number of protons, electrons, or neutrons. So what we really need to know is how many of those parts are in a given atom. Then we'll have at least some idea of its relative size compared to other atoms if we know how many parts make up those atoms. Here are examples. The oxygen atom has 8 protons, 8 neutrons, and 8 electrons. The hydrogen atom has only a single proton and a single electron. Most hydrogens don't have any neutrons. Clearly, the oxygen atom is much heavier than the hydrogen atom. As I mentioned earlier, if you take the actual mass of a proton and a neutron and compare them to within about 3 decimal places, they are equivalent. Its very small mass, 1.67 times 10 to the minus 27th power in kilograms, but they're still very close to each other. And also, very significantly, they are much larger than electrons. Electrons are over 1,800 times less massive. Consequently, we can ignore electrons most of the time as far as the mass of an atom goes. So if protons and neutrons weigh almost the same amount, scientists decided that might be a good fundamental unit of measurement, and so they derived something called the atomic mass unit, which is approximately 1 proton or 1 neutron's mass. So the atomic mass unit, which we will abbreviate AMU, is equal to 1 when you have a proton, and it's equal to 1 when you have a neutron. So in hydrogen, we had 1 proton. It must weigh 1 atomic mass unit. It had no neutrons, and you can ignore the weight of the electron because it's so small. The oxygen, on the other hand, had 8 protons, that's 8 atomic mass units, and 8 neutrons, 8 more atomic mass units. So an oxygen atom must have a mass of 16 atomic mass units, 16 times more massive than the hydrogen. Now that we know that oxygen weighs 16 atomic mass units, we can count oxygen atoms by weighing them. We could do a little conversion problem. That's our goal. We want a substitute for counting. We think that by weighing or taking the mass of something, we should be able to do a conversion and get a count. The problem here is that our mass unit is the atomic mass unit, and we don't know what that is. It's really, really small. It's much too small for us to actually measure in any practical sense in our lab. So, if you go to a chemistry lab, you'll find balances or scales that measure units called grams. So what we need is another conversion factor, one that converts between atomic mass units and grams. So the question is, how many atomic mass units are in 1 gram? If we knew that equivalence, we could use it as a conversion factor. And we could now find how many protons and neutrons are in a given element's atoms, do a couple of conversions, and then we could get a count by weighing. Turns out that we know what the equivalence is. 1 atomic mass unit equals 1.66 times 10 to the minus 24th power grams. It's really small. But what we really find useful is to turn that around and say, if I had 1 gram, how many atomic mass units would that be? So what we do basically is take the inverse of 1.66 times 10 to the minus 24, and we find out that 1 gram is equivalent to 6.02 times 10 to the 23rd atomic mass units. 6.02 times 10 to the 23rd is a very large number. It's a 602 and then 21 zeros. That's how many protons or neutrons it takes to make 1 gram of anything. It turns out that this number, 6.02 times 10 to the 23rd, is very important in any gram of any substance. There are 6.02 times 10 to the 23rd protons and neutrons. That's an equivalence that we can use to convert between mass and counts. It does not matter what the element is that you're looking at. This is the same number for all substances. So, what we really need to know if we want to calculate the number of atoms in something is which atoms are present, how many atomic mass units are in that atom, and then we'll take this equivalence, 6.02 times 10 to the 23rd protons and neutrons equals 1 gram, and we should be able to count by weighing. Just a little digression here. If I wrote this number down for you and asked you to say it, pronounce its name, you would say 1,000. This is 1 million. This is 1 billion. And this is 1 trillion. Now, you no doubt learned those names back in elementary or middle school. What about this number? Look at 1 trillion has a 1 followed by 12 zeros. What if I had a 1 followed by 100 zeros? Does that have a name? It sure does. It's called 1 Google. You're right. Google. That's where the name of the company came from. Someone said, we are going to have a whole Google of data bits of information when we get this internet set up. And somebody said, that's a great name. Now, what about this number? 6.02 times 10 to the 23rd power. How would you say that number? Believe it or not, you say it Avogadro's number. What? Yes, that's its name. It has an official name, just like 1000 has a name. 602, followed by 21 zeros, is called Avogadro's number. It was named in honor of Amadeo Avogadro, who was a chemist in the early 1800s, and he was famous for studying gases, the properties of gases. And so I'll explain a little bit more in a later video, the connection between his name on this number and the study that he conducted. So, can we count atoms by weighing them? Let's say I have 12 grams of pure carbon-12. All the other types of carbon, carbon-13 and carbon-14, have been removed. How many carbon atoms do I have if I have 12 grams of carbon? I'm trying to count by weighing. So I've weighed it, I've got 12 grams, now I want to count. Well, that isotope number, 12, tells me there are 12 atomic mass units or particles in carbon. There are 6 protons and 6 neutrons, a total of 12 particles. So, if I know that 1 gram of matter has Avogadro's number of protons and neutrons, I could set this up as an equation like this. Let me write what I have on the left. That's 12 grams of carbon. I'll write what I want to find way over on the right. I want to find a count of carbon atoms. And in between, I can do one or more conversions. The first conversion that would be useful is to note that in 1 gram of any matter, including carbon, there are 6.02 times 10 to the 23rd protons and neutrons. You might notice that the grams of carbon on the top and the grams of carbon on the bottom are ultimately going to cancel each other. So I like to cancel them out as I go so I can pay attention to what units I'm working with. The units that I'm left with is protons plus neutrons. That's not the units that I want. I want a count of carbon atoms. That means I need to do another conversion factor. The other one that we've mentioned is that 1 carbon atom has 12 protons and neutrons. Now the protons and neutrons are going to cancel, and I'm going to be left with carbon atoms, which is exactly what I want to find. All that's left to do is to do the math. Now before you pull out your calculator, I always like for you to first try to estimate an answer. But in this particular case, you can actually calculate the answer because you see that 12 on top and 12 on bottom of the fractions. Those will cancel out. So all you're left with is 6.02 times 10 to the 23rd. Even the ones are going to cancel out. But you're also left with carbon atoms. So I always have 3 parts to my answer. I have a number, a unit of measurement, and a substance. In this particular case, my unit is simply a count. 6.02 times 10 to the 23rd power carbon atoms. In other words, in 12 grams of carbon-12, there are Avogadro's number of carbon atoms. That seems like quite a coincidence. Is it? Not really, but it's a useful piece of information because now I can use this equivalence. Anytime you find an equivalence, you can use it in your next conversion problem if you find it helpful. What if you were given this problem? What if I had 108 grams of carbon-12? Now how many carbon atoms do I have? Let's just use our equivalence written at the top of the screen. 6.02 times 10 to the 23rd carbon atoms equals 12 grams of carbon. The grams on top and bottom are going to cancel each other. I'm left with 108 divided by 12 times 6.02 times 10 to the 23rd power. Now I don't know exactly what 108 divided by 12 is maybe, but I can see it's probably a little bit less than 10, so this number is going to be bigger than 6.02 times 10 to the 23rd, and in fact it turns out to be 5.42 times 10 to the 24th power. I'd like for you to estimate first, so we see that we should have gotten a power that's at least 10 to the 23rd, but probably bigger. So, by weighing the carbon, doing one step of mathematics, I was able to get a count of carbon atoms. That's my goal. I want to be able to count by weighing. We know that 12 grams of carbon contains Avogadro's number of carbon atoms. Can we find a similar equivalence for other atoms? Sure you can. If you had Avogadro's number of hydrogen 1, that would weigh 1 gram. If you had Avogadro's number of oxygen 16, that would weigh 16 grams. If you had Avogadro's number of calcium 40, that would weigh 40 grams. If you know the isotope number, then you know an equivalence that will help you count by weighing. Yay, that was my goal. By knowing that there are Avogadro's number of protons and neutrons in 1 gram, I can now count atoms by weighing them. I just have to do a little bit of math. It's time for you to do a little bit of practice. There is a worksheet associated with this video. I hope you have access to that. And in the next video, we're going to take this concept just a little bit further. Instead of dealing with pure isotopes, what if we have a random sample of an element? That's what we will do next.